Hello, everyone, and welcome to the third and final workshop of the day. This workshop is going to be focused on getting started with ICP. And to lead this workshop, we have Morritz from the Dfinity Foundation to take us through. So Morritz, I will pass it over to you.
Thank you. Hi, everyone. As already mentioned, my name is Morritz. I'm a developer relations engineer at Dfinity. And today I'm going to give you a quick intro about what the Internet Computer is. And then we're going to take a more specific look at the Bitcoin direct integration, at the threshold signing capabilities that the Internet Computer offers, and then also at CKBTC, a synthetic Bitcoin twin token issued on the Internet Computer and secured also by the threshold signatures that I mentioned just now. So throughout the slides, there are a couple of QR codes that you can scan if you want to get to further reading materials. And the first one is actually on this slide here, and that gets you to the deck that I'm using today. So in case you want to read up on something or you want to get a better look at one of those QR codes, now's your chance to get access to the presentation. So you don't have to keep your phone out all the time trying to scan them. It's probably a bit easier. You could actually also click on them. They are also hyperlinks. Okay, I guess that's enough time to scan this one. So let's dive in. So for those of you that are not aware yet, the Internet Computer is a decentralized and permissionless cloud built on blockchain technology. And I want to start with a quick topology overview. So what you see here is basically a simplified version of what the Internet Computer tech stack or protocol stack looks like. So at the bottom, what we see, those black cubes, those are data centers, and they are distributed around the globe. And within those data centers, so-called node providers run nodes. Those are the gray boxes that you see. I think I have a pointer. Yeah, perfect. So those are the data centers, the black cubes. Then on top or within the data centers, node providers run nodes. And the nodes then again form so-called subnets. And every single node, so every gray box here, can only be part of one of those subnets. And when I say subnet, what you can think about is basically an independent blockchain, so a replicated state machine. And that means that every node within a subnet performs the same computation on the same state. And as you can see already, the Internet Computer doesn't consist of a single subnet, but of many subnets. And they all run in parallel. This is a little bit, I think, what Ethereum had in mind when they wanted to implement sharding. I think they moved away from that, and now they have this layer 2 scaling solution, at least for now. But I think this is essentially very, very similar to that idea. And the cool thing about those subnets is that they can seamlessly communicate with each other. And that, of course, also means that a smart contract, or what we call a canister, those are the containers that you see within the subnets, they can communicate seamlessly across subnets. And this is also the feature that allows the Internet Computer to scale horizontally. So if the Internet Computer Protocol needs more computation or more storage, what it can do is to basically take idle node providers and group them together and make them form a subnet, and that again then adds more storage and more compute to the network. All right. And because the Internet Computer is easier to think about as a decentralized cloud, it's also easier to think about canisters or smart contracts as decentralized servers. And there are a couple of capabilities that canisters on the Internet Computer have that are special, I would say, and that you don't usually get on other layer ones. And I'm not able to talk about all of them today in depth for the sake of time. So I'm just giving you a quick rundown. for the ones here on the slides. So we have timers. It's the first one up here. And timers allow canisters to execute code either periodically or after a certain amount of time has passed. So you could, for example, say, Internet Computer Protocol, please execute this function on my smart contract every 5 minutes, or you could say, please execute this function a year from now. That's basically this feature in a nutshell. Then we have the so-called reverse gas model. That means that instead of letting the user pay transaction fees, actually the deployer of the canister or the deployer of the smart contract pays for the fees or for the computation that's incurred. And this is done by a developer when they deploy a canister, by charging up that canister with cycles. This is what we call gas in the Internet Computer ecosystem. The next feature is that you can, from a canister, call into Web 2 without the need of a central or an external Oracle infrastructure. And it's pretty much really that feature. It's basically making an HTTP outcall from a smart contract. So you can say what you want to call, you can provide a payload, you can decide whether you want to make a GET or a POST HTTP request, you can provide headers, and so on and so on. So very common Web 2 stuff, but not usually available in the context of a blockchain. The next feature is, it's basically more a capability of the system, and that is that smart contracts are able to operate at web speed. So when you send a message to the Internet Computer and it gets processed, it takes roughly 1 to 2 seconds until that message is finalized. So if you are building a dApp, you can really build a dApp that caters for a good user experience, because your users don't have to wait basically until a message is finalized. And usually when they interact with a dApp deployed on the Internet Computer, they don't realize that it's currently running on a blockchain. And that is due to the reverse gas model, so they don't need to have any ICP or something, and also due to the fact that it's very fast when processing messages. Then we have on-chain randomness. So that's also usually something you need an Oracle for, but in our case, the Internet Computer provides that. That's also a very neat feature for a number of use cases. Next thing, this is what we are going to touch up on in depth today, are the chain key signatures. And here we have threshold signing capabilities for ECDSA and also for Schnorr. Both signature schemes that are supported by Bitcoin, so very important to have. And this feature basically means that a canister is able to natively hold Bitcoin, Solana, or Ethereum, basically any layer 1 or layer 2, any chain basically that supports those signature schemes. The funds from those chains can be held within a canister or by a canister. Then storage. Canisters have access to a very big amount of storage. So currently a single canister can hold up to 500 gigabytes of storage. It's also pretty neat. Usually something that's more expensive on layer 1s, even these days. And then last but not least, canisters can serve web. So you can take your assets from a website, so the HTML, CSS, JavaScript, images, I don't know what, and you can push it into a canister, and the canister can then serve this into a browser without users kind of like needing to download any special software or something like that. It just works natively because they are able to serve web, they are able to serve HTTP. All right. So what I'm mostly talking about today is communicated by us, or can be captured by the term chain fusion. That is a very broad term, kind of like an umbrella word that we nowadays use to describe the many things that are all aimed to fuse the Internet Computer together with other chains that are out there. And the overall idea of chain fusion is that we want to enable developers to leverage the properties of multiple chains within a single dApp. So we want to bring the strengths of the Internet Computer to smart contracts on other chains, and also vice versa. And as of today, we support basically all or most EVMs or EVM-based layer 2s. We have a Bitcoin direct integration that we are talking more about today. And we are also currently working on supporting Solana. And this should be ready this year. So we're not focusing on all of this. We are basically focusing on chain key ECDSA signatures and chain key Schnorr signatures, the Bitcoin adapter, and then also on CK BTC. This is also the order of the presentations, I think, at least. Yeah, I think first we talk about signatures, the adapter, and then CK BTC, and that should be correct. I mean, because this is a hackathon focusing on Bitcoin, right? I unfortunately don't have time to touch up on the EVM stuff, but there are YouTube playlists out there that go through them. So if you're interested, you can check that out as well. And they are available in the following the 2 QR codes here in the top right corner. All right, so yeah, basically, what you need if you want to integrate with another layer 1, if you think about it, are 2 key building blocks. So you somehow need to be able to read state from the chain, and also you need to be able to write state to that chain. So secure, as it's written on the slide, securely reading from and writing to other chains of interest. And what you need for that in the case of Bitcoin is you need to be able to verify the consensus of the other network within the internet computer. And you also need to be able to sign a transaction for Bitcoin. And this is where we use threshold ECDSA and threshold Schnorr. And in the case of other chains, other EVM chains, we don't have this direct integration. This will become a bit more clearer throughout the presentation. What we do is we use this HTTP outcalls feature that I talked about earlier. And here, we basically make an HTTP outcall to a number of RPC providers for that specific chain to read state. And then what we do is we make consensus on the results that we receive from those different RPC providers, so that we do not rely on a single RPC provider that might become faulty or malicious or whatever. We ramp up the security here by talking to multiple RPC providers. But out of scope for this talk, still wanted to mention it though. So yeah, what you need, the Bitcoin direct integration and threshold signature schemes. And of course, your Canister smart contract to tap into those 2 capabilities. So I mentioned it a couple of times already, the Bitcoin direct integration, but what actually is that? In one sentence, what the Bitcoin integration does is it allows canisters on the internet computer to receive, hold, and send Bitcoin, all directly with transactions on the Bitcoin network, on the layer 1 Bitcoin. And to better understand why this is quite nice, we have to take a look at how things used to work, or most of the time still work today. So how does it actually work if assets from other chains are available or are made available on a target chain? I think a good example, as we're talking about Bitcoin, is RepBTC on Ethereum, which I think still has the most Bitcoin locked when it comes to making Bitcoin's liquidity available on other chains. But when you are using Bitcoin on Ethereum, you're actually trusting 2 groups of people. There are the custodians that hold the assets, in that case Bitcoin, and there are the merchants, and those are the only ones that are allowed to mint or to burn RepBTC. And even though usually when you go to the RepBitcoin website, they say that the custodians, it's actually, last time I checked, at least only a single custodian, that is BitGo. So a single company that acts as the custodian of all the RepBTC that are out there. So if you want to mint RepBTC, and thus if you want to bridge your Bitcoin to Ethereum, one of those merchants has to send Bitcoin to the custodian, and that then, upon receival of the Bitcoin, mints the same amount of RepBTC to the merchant, that then gives it to you. And if a user wants to bridge their Bitcoin to RepBTC, they actually have to go to through KYC and AML with the merchant. So usually what happens is they send them the Bitcoin and then wait to receive back the RepBTC. And if you want to go the other way around, so you want to get your Bitcoin back and basically unwrap the RepBTC, you again have to send the RepBTC to the merchant, and then again, usually you have to do KYC and AML, and then wait until you receive back the Bitcoin. And a couple of trust assumptions are in place here. So yeah, you have to trust the custodian, in that case BitGold, not to run away with your funds, not to get hacked, and also to always honor this one-to-one backing of RepBTC with Bitcoin. So maybe you send in 10 Bitcoin, they give you 10 RepBTC, but they, I don't know, spend the remaining 5 Bitcoin that you gave to them, right? You have to trust them, they don't do that. And here what they said is that to kind of like minimize the trust, they say the custodian cannot mint tokens on their own, but they need the initiation of a merchant to do so. But I think should be probably easy to collude here, right? Only 2 players involved. If they really wanted to do it, kind of like print RepBTC out of thin air, they could, but you trust them not to do so. So that's actually also something in the white paper. They say that their framework minimizes trust as the credibility of the institutions involved is at stake. But for me personally, that's not enough of an argument to trust my money with. Anyways, this kind of architecture is called a trusted bridge. So a trusted bridge depends on a central entity for operations, and it has trust assumptions with respect to the custody of the funds and also the security of the bridge. So the users basically rely on the reputation of the bridge operator, and they have to give up the control of the assets. So you have to give your Bitcoin away to BitGo, and they give you an asset that wouldn't be worth anything if it wouldn't be backed by Bitcoin anymore. So you trust that whenever you want to go back, they really have the Bitcoin and they are really going to give it to you. So that's okay, I guess, but not ideal. So now that we know how things used to work, let's take a look at the Internet Computer's direct integration with the Bitcoin network. So what do we mean when we say by direct Bitcoin integration? In this context, direct means that there are no trust assumptions required other than trust in the correct functioning of the Bitcoin network and the correct functioning of the Internet Computer Protocol. So in other words, there are no additional parties required, such as bridges, bridge providers, merchants, custodians, and so on, resulting in a much cleaner and also more secure integration. So in essence, the difference between the existing solutions and the Bitcoin direct integration is that in the case of the Bitcoin direct integration, the actual funds are held directly by a smart contract. So if you know the code and you know that it can't be tampered with and you trust the protocol that it runs on top, you have minimal trust assumptions, I would say. Whereas with solutions like RepBTC, there's always some rather big level of trust involved that you need to be willing to give. And there's always a risk of the custodian or maybe the bridge infrastructure itself being hacked, or some employee turns rogue, or I don't know, whatever. I mean, we've seen it in the past, right? There have been, quite some, quite big hacks that happened in the past that were targeted at bridges or bridge operators. So they are basically a big honeypot because they hold a lot of funds, and therefore are an obvious target for people that are good at doing those kind of things. Anyways, why would this be important? So first of all, It positions the Internet Computer as a Bitcoin layer 2, so it enables programmable Bitcoin. Because a smart contract can hold Bitcoin, you can also have on-chain Bitcoin wallets, so basically smart contract Bitcoin wallets. With things like CKBTC that we are touching upon later, you can actually send funds via, for example, a chat message and SocialFi applications. The idea here is that you really have Bitcoin microtransactions. So you can send a fraction of a second in Bitcoin, and you are not like killed by the transaction fees that usually occur on the layer 1. You can also finally trade Bitcoin runes, BRC20 tokens, and other meta assets on decentralized exchanges, which is also pretty cool. You can build things like lending markets using ordinals or other meta tokens as a collateral, or even Bitcoin. You have things like CKBTC that we will hear a bit about later on. You can have a smart contract managed BRC20 index fund, and so on and so on. And actually, most of the use cases that I described are already implemented, and some of them are quite successful. So, for example, Liquidium is building borrowing and lending on top of DIC. Odin.fun, I don't know if you heard about it. It's like a kind of like a pump.fun style token launchpad targeting runes. That's also built on ICP tech and on Chain Fusion. I have another project that builds an index fund targeting Bitcoin meta protocols. So they are valid. People build them. They have customers. So and they were enabled by this Bitcoin direct integration. So quite cool. All right. So before we dive deeper into the inner workings of the Bitcoin direct integration, I quickly want to explain the concept of a UTXO. And as a simple example here, we have on the left-hand side Alice that wants to send 400K sats over to Bob. And to do this, Alice has to consume the two unspent transaction units, or UTXOs, on the left-hand side here in blue. And they both together add up to the 400K sats that she wants to send to Bob. And the boxed key here is the private key, unboxed key, public key. And this basically indicates Alice, which apparently is very old, sending Bitcoin over to Bob. All right, so what she does is she creates a transaction with the two UTXOs that are going to be consumed as an input, and the new UTXO belonging to Bob produced as an output. And as you can see here, the inputs to this transaction were actually outputs from previous transactions. So if you want to create a transaction on a Bitcoin network, you have to spend UTXOs. And of course, you can only spend UTXOs you are authorized to spend. So basically that you kind of like own. So usually simplified, each UTXO has a public key associated with it. And you basically prove that you have ownership over this UTXO by creating a signature that's associated with the public key attached to the UTXO. This is this blue ribbon here next to the UTXOs. Then in the next step, a number of those transactions hit the network, and they are all together put into a block. Block is mined, they're chained up, and that forms what we ended up calling a blockchain. All right. With that out of the way, let's focus on the two building blocks that I mentioned earlier that are needed to enable chain fusion. So a way of reading and writing from Bitcoin or to Bitcoin, and also, or in general, from a chain, and also signing a transaction. So for reading and writing, we have the so-called Bitcoin API, and that is enabled by a protocol level integration of the internet computer with the Bitcoin network. And that integration allows canisters, so smart contracts on the internet computer, to, for example, fetch balances for Bitcoin addresses, get block headers, get the UTXO that belong to an address, and also to send a signed transaction to the Bitcoin network. We will look at this in a little bit. The next part, the signing capabilities, here we use, or we provide for developers, the threshold ECDSA and threshold Schnorr APIs that are developed in the chain key signatures protocol suite. And this, it's not only the signatures, but a number of other things, like, for example, also the key generation, public key retrieval, and a couple of other things. All right. So let's start with the Bitcoin integration. So basically the way that allows us to read from and write to Bitcoin. Let me quickly go through the functions that it offers. So the ones with the gray background. So the first one is Bitcoin get UTXOs. So the way you imagine this, I'm actually covering this in another workshop I'm doing on Wednesday. That's practical, where we actually look at how to code an application that uses this API. But from a high-level perspective, a developer calls this function, this Bitcoin get UTXOs function, from the smart contract that they are developing. And the first method or function provides, as the name suggests, the UTXOs for an address. Second function, the Bitcoin balance for an address. Third function, Bitcoin send transaction, allows to submit a signed transaction to the Bitcoin network. Then to be able to create a transaction, you need to be able to understand the current fees. So your transaction gets actually ingested. And that's what this Bitcoin get current fee percentiles is for. And then we also have a way of requesting block headers from within a canister. Okay. Let's continue. All right, so this is the high-level API. So pretty basic, right? Just 5 different functions, but they give you, I think, enough to build a lot of things. Yeah, not everything, but give you enough to build most of the things. But let's go a little deeper now and look at how this Bitcoin API is actually implemented. So how is this enabled? How can a smart contract get the UTXOs of a certain Bitcoin address? It actually consists of 2 components. So the first one is the Bitcoin canister. Let me show you that. It's up here. And that Bitcoin canister lives on a so-called Bitcoin activated subnet and is implemented as a regular smart contract managed by the NNS. The NNS is the network nervous system. So the entire intercomputer protocol is governed by a huge DAO. And that DAO is not only responsible for upgrading the protocol, but it also controls a couple of, let's say, system-relevant canisters, like, for example, the Bitcoin canister. And this Bitcoin canister offers the functionality, basically the API methods that I showed you on the previous slide. And as a developer, you just basically provide the address of this canister, and then you can call the interface it provides. So very straightforward, nothing fancy going on here. It's the same as an Ethereum developer calling another Ethereum smart contract from the contract they are implementing, right? So nothing fancy. And that Bitcoin canister, to be able to facilitate or provide this API, needs to hold the on-chain Bitcoin related state. And that is, for one, the full UTXO set. Whoops, you can see this up here. Outgoing transactions. This is needed for this send Bitcoin transaction endpoint that we saw on the previous slide. And also the most recent Bitcoin blocks to allow for fork resolution. And so this is basically on the application layer. This is what the developer integrates with. And then in the protocol layers below, we have the so-called Bitcoin editor. That's right here. And that Bitcoin editor runs on every node, so on every physical machine that is part of the so-called Bitcoin activated subnet. And the editor is connected to other nodes within the Bitcoin network, much like a regular Bitcoin node. And through this Bitcoin adapter, the internet computer is able to obtain Bitcoin blocks directly from the Bitcoin network and process the contained transactions therein. So how does it work that this Bitcoin canister up here has access to the full UTXO set on chain? I mean, part of it is because, as I mentioned in, I think, the first slide, that the internet computer gives canisters or smart contracts 500 gigabytes of storage. So it is indeed possible to hold the full UTXO set within a single canister, because I think it only has 10 gigabytes or something. And then you have to build some indices on top so that you're able to query it efficiently. And then I think in total, it adds up to 100 gigabytes or 110 or something like that. So a lot of room to grow. So yeah, this on-chain UTXO set is managed by the Bitcoin canister and the Bitcoin adapter communicating through the internet computer's protocol stack. And the process here starts with the Bitcoin canister requesting successor blocks to the latest block that it received from the Bitcoin adapter. And then the Bitcoin adapter, as I said, running on each replica of a subnet, obtains the latest block from the Bitcoin network. And then next, this is a bit technical now, the block making replica for this round, so basically the leader for this round, provides the requested blocks to the Bitcoin canister through consensus. So all the nodes in the subnet, in the Bitcoin activated subnet, have to agree that basically the requested blocks are the blocks that they see as well. And once the Bitcoin canister receives that block, it extracts the UTXOs from the transactions contained in the blocks and then updates the UTXO set it maintains in replicated state. And that's a mechanism that allows for maintaining the full Bitcoin UTXO set on chain. And the same mechanism is also used to get things like the block headers into the Bitcoin canister. And for the Bitcoin get current fee percentiles, the last 10,000 transactions that the Bitcoin canister saw are analyzed to give developers an idea of what fees are currently like. Yeah, I mean, I think having something like this on-chain is, again, quite unique to the internet computer because, yeah, usually you don't have storage capabilities that are that big. So yeah, I think it's a pretty cool solution to this problem. Anyways, so what we covered now were the Bitcoin get UTXO method, because we have the full UTXO set in the canister, the Bitcoin get balance, because that can be calculated from the UTXOs. But what about, also we talked about the fee and the headers, but what about the Bitcoin send transaction endpoint? So if a canister wants to submit a Bitcoin transaction or send a Bitcoin transaction, it is submitted to the Bitcoin canister, where it's actually queued. And that's this arrow here, send transaction. And those are the queued transactions here. And then every subnet round, the Bitcoin adapter on all of the replicas, so basically all of the nodes in the subnet, obtain the pending transactions or fetch the pending transactions from the Bitcoin canister and then queue them for being submitted to the actual Bitcoin network. And a cool side effect of this is that it leads to a very efficient and very quick distribution of transactions in the Bitcoin network, because every replica in the Bitcoin activated subnet, so every physical machine in the Bitcoin subnet, runs this Bitcoin adapter, and the Bitcoin adapter connects to a random subset of nodes in the Bitcoin network. So you get a very, very big distribution of your transaction, which is also nice. All right, so that was the first key building block, how to securely read from and write to Bitcoin. Let's talk about the other key building block, and that is how we can securely sign transactions for the Bitcoin network. And that is enabled by so-called chain key signatures. And they consist of a threshold signature scheme where the private key is shared across the nodes of a subnet. So those chain key signatures, we touched on this, come in two different flavors. So we have threshold ECDSA and threshold Schnorr signatures. And what I mean by shared across the replicas of a subnet is that the secret key, basically the signing key, is split into secret shares. And each one of those shares is stored on a different node in the subnet. And of course, this is done in a high replication factor subnet. So there are app subnets that have a lower replication factor, and then there are system subnets, fiduciary subnets, the DNS subnet, and so on and so on. And also this signing subnet, and that has, in comparison to the app subnets, I think roughly 3 times higher replication factor. So to sign a message, the nodes in the signing subnet must coordinate to generate the signature in a distributed fashion. So at least 1/3 of the nodes are required to jointly create a signature using their respective key shares. And that way, canisters have control over a unique ECDSA and Schnorr key pair, and they can request signatures with the corresponding private key to be computed. And from this single key pair, basically an unlimited number of keys can be derived. So it's not like there's a single Bitcoin address for a canister. No, canisters can actually derive basically an unlimited amount of keys and therefore an unlimited amount of Bitcoin addresses. And this is very helpful, as we'll see later when we take a look at the CKPTC meter. So what's important to take away here is that the private key never exists in reconstructed form, but only in its secret shared form, even when signing messages, and that this feature enables canisters to natively hold Bitcoin, Solana, Ethereum, and any other assets that support either ECDSA or Schnorr signatures. And this is the API for ECDSA. It's a bit dry, so on the left-hand side, this can be used to derive a ECDSA key, a public key, of course. And on the right-hand side, this is used to create an ECDSA signature. On the left-hand side, maybe important to highlight is that here you can provide a canister ID. That's basically the address of a smart contract as an argument. So I can, if you are the developer of a smart contract, I can, of course, see what's the public key, the ECDSA public key of your canister. But when it comes to signing, of course, I cannot trigger a signature from your canister. So in this case, if you call this the caller of this function, and that is always a canister, is derived. So only a canister can create signatures with its own kind of like ECDSA key pair, but not on behalf of others. And that makes sense. And for chain key Schnorr, it's basically the same thing, right? One function to derive the public key on the left-hand side, and another one to actually create a signature. You can take a look at this in detail using the QR codes, but I realize I'm a bit slow today, so I'm not going into more detail here. Okay, so for you as a developer, how would it look like if you wanted to leverage that Bitcoin integration? And we can take a look at the full flow here and what it would look like if your canister already held Bitcoin in its address, in its Bitcoin address, and it wanted to send a Bitcoin transaction on the Bitcoin network. So what we start with is that the canister here gets the UTXO it owns, and also the current transaction fees by calling the Bitcoin get UTXOs and providing its canister ID or address as an argument. And then it knows, okay, I got this UTXOs and I can spend so much. And then also the Bitcoin current fee percentiles. And those two are enough to create a Bitcoin transaction. So I specify the UTXOs and I specify the fee that I'm willing to pay. But creating the transaction is, of course, not enough because we have to prove ownership of those UTXOs. So we have to create a signature. And here, of course, we call the sign with ECDSA or sign with Schnorr functions that we saw earlier. And then once we did that, we have a signed Bitcoin transaction. And we can then take this signed transaction and send it to the Bitcoin network via the Bitcoin send transaction function that we saw in the Bitcoin API. And then the nodes in the subnet and the Bitcoin activated subnet through the Bitcoin adapter relay our transaction to many other nodes in the Bitcoin network. And that's basically it. So at a high level, from a high level perspective, very straightforward and relatively simple, I would say. So on top of that, we built CKBTC, Chain Key Bitcoin. And that is mainly because even though they're quite simple, still the Bitcoin API and also the threshold signing capabilities, they're a bit low level, and they of course require you to have some understanding of how Bitcoin works and some understanding on how to properly create a transaction and sign it and so on and so on. And also, of course, because every transaction happens on Bitcoin, transactions are rather expensive and also rather slow. So if you only want to tap into the liquidity of Bitcoin and you're not really kind of like looking into use cases where, I don't know, you want to create a specific Bitcoin transaction to, for example, etch a rune or something, then maybe for you it's enough to just use CKBTC to tap into that liquidity and then use CKBTC within your dApps infrastructure. So yeah, CKBTC, as I mentioned all the way at the beginning, is a synthetic twin token on the Internet computer that has a much stronger underlying trust model than existing wrapped or bridged Bitcoin versions because of its decentralized architecture that was designed to build on top of chain fusion instead of building on top of centralized bridges. And as I said, a lot easier to integrate with this if you just want to tap into Bitcoin liquidity, because it's actually just, if you integrate it with a simple ledger, right? Like any other ICRC1 ledger on the Internet computer, ICRC1 is the equivalent of ERC20. So you just, talk to a ledger basically when you integrate with it. And of course, because it's running on the Internet computer, you benefit from the power of the underlying network. That is that transfers are very fast and have a fast finality, so 1 to 2 seconds. And also the costs are super low. So there are no transaction fees because we have the reverse gas model, but you have a ledger fee, and that is 10 sats. So roughly, I think either 0.1 cents or a cent to facilitate a Bitcoin, a CKBTC transfer on the Internet computer. So if you use CKBTC, only the settlement transfers are on the Bitcoin network. So basically, when you go from Bitcoin into CKBTC, that's of course a transaction on the Bitcoin network because you send your Bitcoin funds to the CKBTC minter. And then the other way around, if you want to get your Bitcoin back and get out of CKBTC, again, to send you your Bitcoin on the Bitcoin network, of course, the CKBTC minter has to create a Bitcoin transaction. But the majority of the transfers can be done with the lightning speed and the low cost directly on the Internet computer. And in this architecture that we see here, there are a number of different components involved. So we have the CKBTC minter that I briefly mentioned. We have the CKBTC ledger. This is this ICRC1 or ERC20 equivalent smart contract or canister. And we have the Bitcoin canister. This is actually gone by now that I see this slide again. So I'm not going to touch up on it too much. But yeah, so let's start with the CKBTC minter. So the CKBTC minter holds the actual Bitcoin on the Bitcoin network and is responsible for minting and burning CKBTC on the CKBTC ledger accordingly. So when you want to get CKBTC, you have to give it Bitcoin on the Bitcoin network, and then it will mint CKBTC for you on the Internet computer. And if you want to get rid of your CKBTC and you want to get Bitcoin, it is going to burn your CKBTC and send Bitcoin that it owns or that it controls on the Bitcoin network to your address. And yeah, CKBTC ledger, I guess, is obvious, right? It's used on the Internet computer to record balances and facilitate CKBTC transactions. Then the Bitcoin canister, this is the canister that offers this Bitcoin API that we saw. And this is, of course, used to get UTXOs, so to understand what UTXOs does the minter own. So that way it becomes aware of the fact that you send it Bitcoin. And then it's also responsible to facilitate those Bitcoin transactions. So when you want to go out of CKBTC, it will, like I said, burn the CKBTC and then make a actual Bitcoin transaction on the Bitcoin network, and therefore it uses this Bitcoin send transaction API that the Bitcoin canister offers. All right, and then of course, what's also not shown here is that the CKBTC minter, before sending such a Bitcoin transaction, signs it using chain key signatures. In this case, I think it's actually threshold ECDSA signatures. All right, so now that we have a better understanding of what CKBTC is, let's see how it actually works by looking at the process of converting Bitcoin into CKBTC in a bit more detail. And here we start off by, as a user, querying the CKBTC minter for a Bitcoin address that is specifically reserved for us on the Bitcoin network. As you can see, what we pass here are two arguments, a owner and a sub account, and the owner is usually kind of like our address, so we call addresses principals, and a sub account is basically a 32-byte array that allows a single owner or a single address to have many sub accounts that it also controls. Anyways, for every combination of owner sub account, the address, the Bitcoin address that I receive is unique. So the Bitcoin address is controlled by the Bitcoin canister, but it is derived from the owner sub account tuple that I pass to this get BTC address here. So this is a Bitcoin address. Now, of course, for the Bitcoin canister to mint CKBTC to me, I have to give a Bitcoin first, right? Because we have to have this one-to-one backing. So as a first step, what I do is, now that I have this address that belongs to me, I transfer Bitcoin on the Bitcoin network to this address. Once that is done, and once I think currently 6 confirmations are there, I then call another function on the CKBTC minter that's called update balance. And that's basically me telling the CKBTC minter, hey, I sent you the funds, they are there. We have enough confirmations. Let's get me some CKBTC. Then the CKBTC minter, of course, doesn't trust you. It has to verify that you really sent Bitcoin to this address that it gave to you. So using this owner sub account pair that you provided in the update balance, it again derives the specific address that belongs to this pair, and it calls the get UTXO method on the Bitcoin canister to check, are there UTXOs associated or owned by this address now? If so, the CKBTC minter knows, yes, you really sent funds to me, to an address that I control, because those addresses belong to the CKBTC minter. So only the CKBTC minter has the kind of like authority to control them, to spend them, to do whatever. And of course, the logic of doing that is written in code, and that code gets turned into a smart contract. So you can take a look at it and you can verify, okay, the code makes sense and there are no shenanigans, no backdoors whatsoever going on. And yeah, that's basically how that works. So once the CKBTC minter saw that there are new UTXOs associated with that address, it will then mint the appropriate amount on the CKBTC ledger to a so-called account identifier, and that is basically a combination of the owner sub-account pair here. So basically, it then gives you CKBTC on your ICP address, so to say. And then it says, okay, you got the funds. And that's it. All right. Now let's look at the other way around. So that is, you have CKBTC already. Maybe you bought it on an exchange, or you previously converted your Bitcoin into CKBTC. It doesn't really matter. Matter of fact, you have CKBTC and you want to get Bitcoin. And that is, of course, fine. So the first thing you do is that you call the ICRC to approve function up here on the CKBTC ledger that basically gives the CKBTC ledger the approval to spend CKBTC on your behalf. Of course, for this, you have to specify an amount. So how much do you want to approve the CKBTC ledger for? Usually that's exactly the amount of CKBTC that you want to convert into Bitcoin, but it can be more. Doesn't really matter. So the CKBTC ledger says, yes, okay, got it. I understand that I'm approved now. So next thing you do, oh no, sorry. You create an approval on the CKBTC ledger for the CKBTC minter. So here you say, I want to approve the CKBTC minter of X amount of CKBTC. So the CKBTC minter can spend this amount of CKBTC on my behalf. Next step, you see this amount tick here. That's because I said, right, it has to be at least, or it can be at most the amount that you specified up here. So the CKBTC minter cannot spend more CKBTC than what you approved it for. And this is what's in this bubble here. It doesn't need to be the same than in the ICRs2 approved. Bitcoin address can be arbitrary. Yeah, that's another fact. You also say where you want to receive the Bitcoin to, right? You say to the CKBTC minter, I want, I don't know, 5 Bitcoin to this address. And then what the CKBTC minter does is, of course, it doesn't just randomly send you the 5 Bitcoin to the address that you specified. It first has to check, does this guy even own the same amount of CKBTC so that I can actually make this transfer? And this is happening through this ICRC2 transfer from. And what this is, or what this does is the CKBTC minter is going to burn your CKBTC that you approved it for on your behalf. And if that call works, if the CKBTC doesn't return an error, if the CKBTC ledger doesn't return an error, so if you basically approve the CKBTC minter for enough CKBTC, then this call works. It will burn your CKBTC. CKBTC minter is happy. It knows, okay, this guy CKBTC I burned. I can now send the Bitcoin on a Bitcoin network to this user. But it doesn't, because that wouldn't really scale well. It doesn't, like, for every tiny dust that someone wants to withdraw from CKBTC to BTC, send it to them. It actually aggregates them, right? So on a timer, it checks, let's say, every 10 minutes who wants to withdraw from CKBTC to BTC. And then it sees, okay, there are, I don't know, 20 guys now that want to kind of like withdraw their Bitcoin again. And then it creates this single transaction because all the UTXOs are under its control. It signs all of the UTXOs with the sign with ECTSA function or with a threshold signature. And then it takes the transaction and sends it. And then on the Bitcoin network, the user receives their Bitcoin. All right. Let's see if I missed anything. Nope, looks good. That's actually already it. But yeah, I see we only have 4 minutes left. So if you want to understand more or if you need help, there are a couple of good resources here. So the first one is a hackathon cheat sheet. This is basically a big collection of resources that are really helpful when you are building on the IC. I would really recommend you to check this out. Then we have a developer forum. Yeah, here you can hang out and ask, let's say, more specific and maybe a bit more lengthy questions. This is a direct link to the Bitcoin integration documentation. This is a video series about Chain Fusion, where we only talk about Chain Fusion regarding Bitcoin. If you want to apply for a developer grant, this is the link for this. This is a basic intro to the Internet Computer, also a playlist. And this is when you are an Ethereum developer building on the Internet Computer for the first time. Basically an article which can be quite helpful. And then there's also developer Discord, and the link to that is basically just discord.internetcomputer.org. I should also put this link on this slide. Yeah, I have a couple of minutes for questions, I think. Let me check the chat. I'm actually not sure if I have a chat, but I don't see any comments. So maybe no questions.
Hey, Morritz, I just joined with you. There hasn't been any questions in the YouTube chat, which I've been monitoring, but there has been some in the Telegram chat. So I linked the Telegram into the YouTube comments. For anyone who wants to get in touch with you, I'm pointing them to the ICP challenge chat within the Telegram. Is there anything else that you needed to cover?
No, that's it.
Okay. Awesome. Well, thanks for giving that overview. This has been recorded, and I'm going to share this recording in the Telegram group. And this concludes our third and final workshop of the day. So thank you, Morritz, for leading us here. And thanks for everyone for tuning in. And we will be back at it tomorrow. So it is time to get building. And I will see everyone for our first workshop that will be kicking off tomorrow afternoon.
Awesome. Yeah, thanks for having me. It was a pleasure.
Thank you so much for the overview.
Go check out the Telegram now.
Yeah, perfect.
Bye-bye.
Thanks, everyone.